Hello, very good morning to all of you students. Dear students, let us start a new topic, and that is from Atomic Fluorescence Spectroscopy. So the short form of this Atomic Fluorescence Spectroscopy is AFS. That is, we know that the Atomic Absorption Spectroscopy is denoted by AAS. In the similar way, the Atomic Fluorescence Spectroscopy is denoted by AFS. Before going to learn in detail, let us know what is meaning by atomic fluorescence. So fluorescence is nothing but a radiative phenomenon. So radiations are absorbed, emitted, reflected by the different species, chemical species. These chemical species may be either atoms, molecules, free radicals, then ions, etc. And accordingly, the name of that spectroscopy will be changed. So what is this atomic fluorescence actually? So we know that when any chemical species is irradiated with a photon or radiant energy, that radiant energy is get absorbed by the absorbing species, and when this radiation is absorbed by the chemical species, in this case our chemical species are atoms, and hence the name atomic fluorescence spectroscopy. When these atoms are absorbing radiations from a source, they are get excited to higher electronic energy level. We know that this is the type of electronic spectra or electronic spectroscopy, and all the atoms of a chemical species are at room temperature, they are at a particular energy level. Let us consider all these atoms previously are present at a ground state energy level. So when these ground state energy level atoms are absorbing radiations, they are get promoted, their energy is get increased, and they are get promoted to higher electronic energy level. They are getting promoted to higher electronic energy level. So this is depicted in this figure. So this is first figure. Okay, so this is ground state. 0 is indicating that the atoms are present in the ground state electronic energy level. When they are absorbing radiations, A is standing for absorbance, they get promoted to higher electronic energy level, which is indicated by first excited state, that is 1. Okay, so all the atoms are now in this state. So they are absorbing particular frequency, particular energy, or particular wavelength of light, or particular wavelength of that radiation. When these excited atoms, we know that excited state of any species is always having less time, or lifetime of that state is very less, and hence they are trying to return to their lower energy state, that is ground state energy state. Okay, so when these excited atoms returns to their ground state, which is of lower energy, they emit radiations. That is the excess amount of energy which is present at this state, they are radiated, okay, out of the system. Okay, and that radiations is nothing but fluorescence. When the excited atoms in the higher electronic energy level, they emit radiations, and coming to the ground state in electronic energy level, that emitted radiations are in the form of fluorescence. They are in the form of fluorescence, which is indicated by F. Okay, so here this is the concept of atomic fluorescence. Okay, so this fluorescence may be in the form of light. If it is in visible or IR or UV range, then we can able to see the light is emitting by that chemical species. Here the atoms are able to radiate that light. Okay, and that light is called as fluorescent light, okay, or fluorescent radiation, okay. So this is the concept of atomic fluorescence. Now, as the atoms get excited to higher electronic energy levels, they come across with different modes of fluorescence. They come across with the different modes of fluorescence. We call them as a types of fluorescence. Okay. So here the different 4 types of atomic fluorescence have been depicted in this figure. Let us start with the first. There are actually 4 types of atomic fluorescence. First one is resonant, direct line, stepwise, and fourth one is thermally assisted atomic fluorescence. Okay. So let us start with the first. So what is meant by resonant atomic fluorescence? It is very simple, and in most of the atomic fluorescence spectrophotometers, that is in AFS spectrophotometers, this resonant fluorescence have been identified or have been measured. Okay. So what is this actually? It is very simple. The atoms are in ground state energy level, electronic energy level. They are absorbing radiations from the radiation source, get excited to the higher electronic energy level at the, let us say, first excited state, okay. And this is unstable state, so that's why they are trying to return to their ground state energy level, okay. And while falling down to the ground state energy level, they emit radiations, and that radiations is of same wavelength, to that of the absorbed radiations. Means what is the resonance? We know that the meaning of resonance, when the frequency or wavelength of any two species or any two phenomenon, any two processes get exactly match, we call that phenomenon as resonance, and hence the name is given resonant atomic fluorescence. Means what? The wavelength or frequency or energy of that absorbed radiations is exactly same to that of the fluorescent radiation. Okay. So these two are get matched completely, perfectly matched. The fluorescence frequency or wavelength is exactly getting matched, and hence the name resonant atomic fluorescence. Okay. In this case, this is the simple case of atomic fluorescence. Now the second one is called direct line atomic fluorescence. So carefully, when we look carefully this figure, then it is indicating that our atoms are in the excited ground state energy level. They get excited to higher electronic energy level, say second excited state. So our atoms are getting excited to the second energy level, okay, directly. And when these excited atoms returns to the lower energy state, okay, so while falling down to the lower electronic energy state, they emit radiations. That emitted radiations is nothing but fluorescence. But the condition is that they emit radiations while coming to the electronic energy level, which is not the ground state energy level, means the radiations are emitting from falling down the excited atoms to that electronic energy level which is above the ground state energy level, means in simple language 1 to 2, but not from 2 to 0, 0 to 2 excitation or absorption, but we may expect 2 to 0, but this is not the case. Here is the case 0 to 2 and 2 to 1. So from 2 to 1 we are experiencing or we are getting fluorescence. Okay, so in this case the wavelength of fluorescent radiation is longer, that is Here lambda of absorbed radiation is equal to lambda of fluorescent radiation. This is the condition, okay, for resonant. Then in this case, lambda of fluorescent radiation is greater or longer than lambda of absorbed radiation. Okay, this is the condition, means when the wavelength of fluorescent radiation is longer or greater or higher than the absorbed radiation, then it is called direct line fluorescence. It is called direct line fluorescence. Okay, and such condition is called as Stokes fluorescence. It is called as Stokes fluorescence. Stokes fluorescence. Okay, this is the condition for Stokes fluorescence. Lambda F is greater than lambda A. Then the third case is called as stepwise atomic fluorescence. Stepwise atomic fluorescence is nothing but stepwise atomic fluorescence is nothing but atoms are get excited by absorbing radiations from the radiation source, okay, to the higher electronic energy level. Let us say from 0 to 2, directly from 0 to 2. But from second excited state, they undergo some radiationless collision. They undergo some radiationless collision and come to the middle electronic energy level. Okay, say from 0 to 2, this is absorbance, but they are not falling from 2 to 1 or 2 to 0. They are falling from 2 to 1, but this is the radiationless. There is no radiation takes place. Radiationless collisions takes place among the species, and hence from 1 to 0, that is from the fluorescence can occur from the intermediate electronic energy levels of the atoms to the ground state electronic energy level. Okay, and while falling from 1 to 0, they are emitting radiations, and this emitting radiations is nothing but atomic fluorescence. Okay, and this is called as stepwise fluorescence. Why it is stepwise? Here 0 to 2, 2 to 1, 1 to 0. Okay, not from 0 to 2 and 2 to 0. This is not the case. Okay, so that's why it is the name stepwise fluorescence. Okay, now the last one is called as thermally assisted atomic fluorescence. Okay, so look at the picture here, look at the figure. So here 3 electronic energy levels have been shown. 0, that is ground state energy level, first, second and third. Here radiation source is emitting radiations, and that radiations are get absorbed by the atomic species. They get absorbed and they get absorbed these radiations and get excited to the, let us say, second excited state. Okay, here the atoms are already in excited state. This is the second excited state, means it is already in the higher electronic energy level, but they come across, they may collide, these atoms at this stage, they may collide with some chemical species which are in higher energy state, and they are maybe from the flame source. So hence the name thermal. These excited atoms which are present in the higher electronic energy level, they may collide with some chemical species which are in the higher thermal energy state. They may be coming from the flame. Okay, and due to this, exchange of energy takes place, and these excited atoms again excited further to the more or higher electronic energy level, say 2 to 3. Again this is called as radiationless collision. And when our atoms are in the very higher excited state, that is 3, they may fall down directly to the ground state energy level, ground state electronic energy level, or one level above than the ground state energy level, that is first excited state. That is from 0 to 2 absorption is there, 0 to 2 absorption is there, then 2 to 3 this is radiationless collision between the excited atoms and the thermally assisted or thermally excited some chemical species. Exchange of energy takes place, our excited atoms again goes to the higher energy level, and from this there are two chances, they may go directly to the ground state energy level or to the one level above than the ground state energy level. Okay, so here due to these two possibilities, the wavelength of emitted radiations, that is fluorescent radiation, okay, may be longer or may be shorter, may be longer or may be shorter. Here it is there are two cases. Okay, so here due to the two chances, the wavelength may be shorter or may be longer than the absorbed radiations. Okay, so here we can say that lambda, that is wavelength of fluorescent radiation, may be greater than the absorbed radiation, or lambda of F may be less than the lambda of A. Okay, so this is the case we can say that possible in the thermally assisted atomic fluorescence. Now we have seen that what is meant by Stokes fluorescence in the direct line atomic fluorescence, where lambda F is greater than lambda A. If lambda F is less than lambda A, that is wavelength of fluorescent radiation is shorter or less than the absorbed radiation, we call it as a anti-Stokes fluorescence. We call it as a anti-Stokes fluorescence. Anti-Stokes fluorescence. So this is the concept of Stokes and anti-Stokes fluorescence in the atomic fluorescence spectroscopy. So these are the very basic four types of atomic fluorescences that can be found in the atomic fluorescence given by the different chemical species. Okay, now let us start after this the different the apparatus used for the AFS spectrophotometer. The apparatus used for the AFS spectrophotometer is very similar to that of the atomic absorption spectrophotometer. Oh, okay. So the optical diagram and the arrangement of the different types of components that we are used in the AAS, okay, they are very similar to that of the AFS. This is atomic absorption, this is atomic fluorescence spectroscopy. Okay. Sorry. So what are the components that we are going to see? Okay, so as our atoms are absorbing radiations, so there must be a radiation source, let us say lamp. Okay, so lamp is there for the radiation source, radiative or radiation source. Okay, so the light is coming or radiation are coming out of this radiation source. Okay, this is known as entrance slit, from which the light is entering, it is called entrance slit. Again the light is focusing on the sample cell. Okay, light is focused on the sample cell. Here actually what is happening, the measurement of fluorescent radiations are generally done at a perpendicular direction, to that of the incident radiation to that of the sample cell. Okay, so here from the sample cell, our sample is these are the radiated, this is a radiated source. Okay, and here this is the monochromator, this is the direction of rays or radiations coming from the cell. Okay, so that's why we call it as a monochromator. What is the function of monochromator? Yes, to allow the radiations of particularly single wavelength. Okay, then here it is detector. Here it is detector. This is detector, okay, and this detector gives some signals to the electronic part. Some electronic components are there, okay, and these electronic components are giving signal to the readout device, okay. So this is readout device, this is electronic components, okay. So the readout device is giving a graph or spectra, we can say, okay. So this is all about the different types of components that we can see or that we can use in the atomic fluorescence spectrophotometer. Okay, very simple. So radiation source is there, then say, this is slit, there is also again one more slit, we call it as a exit slit, okay. This is sample cell in which we can take the sample. This is monochromator, this is optical system, okay. This is all about optical system. The title is or heading is monochromator. This is detector, which detects the signal which is radiated from this cell, okay. And this is electronic part, okay. Some electronic components are there, and this gives signal to the readout device, or let us say in our modern instruments it is nothing but monitor, okay. So this is the simple or typical diagram. Now which types of radiation source that can be used for the atomic fluorescence spectroscopy, okay, or atomic fluorescence spectrophotometer? Generally both line and continuous sources, have been used for AFS, okay. The intensity of fluorescent radiations must be greater than the absorbed radiations, okay. So in order to improve this characteristics, improve this property of intensity, generally high intensity radiation source have been used in AFS. High intensity radiations have been used. High intensity radiation sources have been used, okay. Different types of line radiation sources have been used, and they may include hollow cathode lamp, then the hollow cathode lamps which have higher intensity than the simple hollow cathode lamps can be also be used. Then second type of is electrodeless discharge lamps. Electrodeless discharge lamps can also be used in these AFS instruments. Then hollow cathode electrodeless discharge lamps. Then lasers, the most important are lasers. Lasers can also be used in the AFS spectrophotometer. And nowadays in recent instruments that are coming in the market from last 4 to 5 years, the ICPs are used as source for the radiation in atomic fluorescent spectrophotometers. What are ICP? That we know that we already seen that ICPs is nothing but inductively coupled plasmas. So what is plasma actually? So plasma is nothing but this is a system in which there is a coexistence of ions, neutral species and electrons, okay. So positively charged ions are there, negatively charged electrons are there, and neutral species of atoms are also there in that system. And such system, when it is coexisting at a time, that system is called as plasma. And this is an inductively coupled plasma is nowadays very emerging or recent source of radiation source for the atomic fluorescence spectrophotometers. Okay, so this is all about the introductory part of this atomic fluorescence spectroscopy, which includes the meaning and the concept of atomic fluorescence, then types of fluorescence, then the apparatus that is used for the AFS, okay, and the different radiation sources that can be used for this AFS. Okay, so in next lecture we will see the lasers as a radiation source in detail. Thanks for watching this video. Have a nice day.